Hello everyone. Let us solve a very interesting question, and this question is asked in the CSIR UGC NET June 2025, and this question from the functional analysis part, and the weightage of this question is 4.75 mark. Okay, what is given in the question? In this question, C01 contains all the real valued continuous function, and it is a vector space, and this vector space is associated with this norm, means with this supremum norm. C01 is a nonlinear space, and we know that when the continuous function space is associated with this supremum norm, then it is a complete nonlinear space, and every complete nonlinear space is called a Banach space. Therefore this C01 is a Banach space. Okay, and what is asking in the question? In this question also there is an operator T. It maps from this Banach space C01 to the Banach space C01, and it is defined in this integral form. It is defined T of f of f at the point x is equal to integral from 0 to x f of t dt for all the x belongs to 0, 1. And the operator t to the power n is equal to the composition of t n times. Okay, these are the composition of t n times. Okay, then we have to verify these four options, whether these options are true or not. First option is saying that there exists a alpha belongs to 0, 1 such that this relation hold for all fg belongs to C01. When this relation holds for a alpha which is strictly less than 1, then the operator is called a contraction, CONTRACTIN. So in the option 1 it is asking whether T is a contraction or not, and in option 2 it is asking whether T square is a contraction or not, and T square is nothing but T composition T. Okay, and in the option 3 it is in the option 3 we have to check the fixed number of fixed point of t. If t bracket f is equal to f, means that f is a fixed point of this operator t, and it is asking how many number of fixed points are in this set, so whether it is a singleton set or not. If it is singleton set, means it is saying that the operator t has unique fixed point. Okay, in the option 4 we have to calculate the norm of t to the power n. Then we have to check whether this limit goes to infinite when n goes to infinite or not. We have to verify these things. So in the option 4 we have to calculate the norm of t to the power n. So before going to calculate the norm of t to the power n, first of all we have to know what is the norm of t. Okay, so let us calculate the norm of operator t. The standard norm of the operator t is defined in this way. Okay, it is the definition. I hope everyone knows the definition of the operator norm of t. So before going to calculate the operator norm of t, first of all we have to calculate the numerator, then we calculate the denominator. So first calculate the numerator. This norm is equal to supremum of f not identically 0 t f at the point x and its modulus. We have to take this supremum, and so therefore first of all we have to calculate this modulus, and this modulus is nothing but this one by using the definition of the operator tf at the point x. Okay, then we will take the modulus inside, so there is less than equal to sign is coming. Then we will take out the supremum of f of t for all the t belongs to 0, 1, and this is nothing but the f norm of f, supreme norm of f. So there is less than equal to sign is coming. Then we will calculate this integral value, but before calculating here the integrand is 1, it is a non-negative quantity. So here our x is belongs to 0, 1. So if we take the highest value, then the less than equal to sign will be maintained. Okay, so the integration value is equal to 1, therefore it is coming f norm. Okay, so finally we concluded that the modulus of t of f at the point x is less than equal to f norm for every x belongs to 0, 1. Then we will take supremum over x belongs to 0, 1 close interval on the both sides on the both sides to reach to this step. Okay, and the in the left hand side this expression is nothing but the norm of TF. So we concluded that norm of TF is less than equal to F norm for every F belongs to C01. So in the particular, if we take F is non-identically zero functions, then we can divide this norm because it is non-zero quantity. So less than equal to will be maintained. So we will reach to this step where F is non-zero, F is non-identically zero. If it is identically zero, we cannot divide. Okay. Then we will take the supremum over F where F is non-identically zero. Then we will reach to this step, and this expression is nothing but the operator norm of T. So finally we concluded that operator norm of T is less than equal to 1. But we will show that operator norm of T is equal to 1. So what we have to do? We have to do that operator norm of T is greater than equal to 1. Then we can conclude this thing. Okay. So to do so, but we know that operator norm of T is equal to this one. Okay. Therefore, to conclude that operator norm of T is greater than 1, first we will calculate that we know that operator norm of T is greater than equal to any function f naught which is not identically 0, T of f naught divided by f naught norm. This thing hold for any f naught which is non-identically 0 because it is the supremum of over every such f, but here we are taking one such f naught. If we will show that this ratio is equal to 1, if we can find an f naught so that this ratio is equal to 1, then our T norm of T will be greater than equal to 1. So this is our target, to find an f naught so that T of f naught divided by T of norm of T of f naught, norm of T of f naught divided by f naught, means we want to find a function f naught which is non-identically 0 and it is a continuous function belongs to C01 such that this ratio is equal to 1. Then we conclude that our T norm is greater than equal to 1 because norm of T naught always greater than this quantity and this quantity is equal to 1. Then we are done. Okay. So this is our target, and that required f naught is this function f naught x is equal to 1 for all x belongs to 0 1. Then the norm of f naught is equal to 1 because at every point it is equal to 1 and its supreme value is also equal to 1. Then we will calculate the T f naught at the point x. It is defined in this way. So the integral value gives x. Okay. Then if we take the supremum over x belongs to 0 1 closed interval, it is nothing but 1. So we concluded that modulus of T of f naught and norm of T of f naught is equal to 1. And we know that the T norm is defined in this way, and this quantity contains all the f which are not identically 0, but our f naught is a particular quantity. So this quantity will be bigger than this quantity, and we know that numerator value is equal to 1 and denominator value is equal to 1, so it gives 1. Therefore we concluded that norm of T is greater than equal to 1. So from equation 1 and equation 2 we infer that norm of T is equal to 1. Now we will move to verify the option 4. Option 4 is asking what? In the option 4 we have to calculate the T to the power n norm, whether T to the power n norm goes to infinite or not. Okay. Let us move to verify it. Means T to the power n norm, but T to the power n norm, T to the power n is defined in this way: T composition dot n times. Okay. Now we will apply a very celebrated result from the functional analysis. It says that if A and B are two operators, then their norm of their composition is less than equal to the product of their individual norms. Okay. So this implies the norm of T to the power n is less than equal to their product of their individual norms n times. Okay. So this gives a norm of T whole to the power n, and but we know that norm of T's value is equal to 1, so it gives 1. So our t to the power n norm is bounded by 1. So therefore its limit value will also be bounded by 1. This implies that this limit value cannot be infinite because it is always bounded by 1. So option 4 is false. I hope that up to this point everything is clear. Now we will move to verify the option 1. We will verify that whether t is a contraction, means we can find an alpha. Suppose we can find an alpha such that t is a contraction. We will prove it by method of contradiction. We will show that this will contradict something. Okay. Suppose that this statement is true, we can find an alpha and this relation is true. Okay. And this relation is true for all fg belongs to 0, 1. It is a main point that for all, not for some fg, it is for all f comma g belongs to c0, 1. So in particular we can take g is equal to 0, identically g0, then we will reach to this step, and it is true for all f belongs to c0, 1 space, Banach space. So in a particular case, if we take non-identically 0 function, all non-identically 0 functions, then we can divide the norm of f to reach this step, and then we will take the supremum of all such non-identically 0 f on the both side, because it is a constant, so it gives alpha. But this quantity is nothing but the norm of t. Okay, operator norm of t. This implies that operator norm of t is less than equal to 1, less than equal to alpha. But we know that our t norm is equal to 1, so we get that 1 is less than equal to alpha. This is a contradiction. Why? Since our alpha is here, is strictly less than 1. Since our alpha is strictly less than 1, but it is saying that alpha is greater than equal to 1. So this is a contradiction. These two cases are contradicting each other. Okay. So therefore our assumption is wrong. Means we cannot find any alpha such that this relation hold for all fg, and where alpha is strictly less than 1, this is not true. Therefore we are getting the contradiction. Hence option 1 is false. Therefore t is not a contraction. So option 1 is false. This means we cannot find any such alpha which is lie between 0, 1, so that this is true for all f and g, so it is a false quantity, and we have already shown that our option 4 is also 4. Next we will verify the option 2, whether t square is a contraction or not. Let us move to verify the option 2. In option 2, what we have to check, whether t square is a contraction or not. Before going to calculate the t square, first of all we have to calculate the value of t square f at the point x, and it is t square is defined in the composition form, so it can be written in this way. Now take this quantity as a function of g, and g belongs to the g belongs to c0, 1. So this is nothing but t of g at evaluated at x is nothing but integration 0 to x g t dt. So it gives this thing. But now evaluate this function at the point t. So it is nothing but integral from 0 to t f of y dy, this thing. Similarly you can calculate the value of g. Okay. Then take their difference and calculate the modulus value to obtain the norm of the t square f minus t square g. Okay. If we do these things, we will reach to this step. Okay. Then take the modulus inside, then there will be a less than equal to sign, and modulus will come here. Then take the supremum of this quantity where y belongs to 0, 1 close interval. Then after taking the supremum, it will be a constant quantity, so it comes out from the integration, and this supremum value is nothing but the f minus g norm. Okay. So we will reach to this inequality. Then after solving this integration value, we will reach to this step where x belongs to 0, 1 close interval. If we take the supremum on the both sides, this quantity and this quantity, in the right hand side supreme value of x square is equal to 1, because the highest value of x is 1, so it gives half times f minus g norm. Okay. In the right hand side we will get f minus g norm divided by 2, and in the left hand side this we will get this supremum value after taking the supremum over x belongs to 0 1 close interval, and this value is nothing but the norm of t square f minus t square g. Okay, and it gives half times f minus g, but here f and g are our arbitrary function, so it is true for all f and g belongs to C01. So this says that t square is a contraction for alpha is equal to half, so therefore option 2 is true. Okay, option 2 is true. Where our option 2 is true means we can find an alpha which is nothing but half, and this relation is true. So our t square is a contraction, it is true. Next we only have to verify the option 3. The set of all the fixed point of t is a singleton set or not. Okay, let us move to verify the option 3. Here we denote this set by S. Okay, we have to calculate whether S is a singleton set, or we have to verify whether S is a singleton set or not. And the definition of t is this one, and it is saying that t of f is equal to f, so it gives what? It should be f of x. Okay, whether we are collecting those f whether where this relation is true. If you observe here, if we take f is identically 0, this relation is true. Why? The right hand side is equal to 0, and in the left hand side if f is a 0 function, integration value is 0, so the identically 0 function is satisfying this relation. So S is a non-empty set and it contains the 0 element at least. Next we will check whether S contains any non-zero, means non-identically 0 element or not. Suppose S contains a non-identically 0 function g and g belongs to S, we are taking. Let us check what is happening. Since g belongs to S and g is a non-identically 0 function, therefore t of g is equal to g. It is the definition of this set. T of f is equal to f. Okay, then we will calculate the t square g. T square g is nothing but t composition tg, and we know that tg is equal to g, and again we know that tg is equal to g, therefore t square g is equal to g. But we know that this relation is true. This relation 4 is true for all f and g. So in the particular case it is also true for g and the 0 function. Both have belongs to the g and the 0 identically g 0 function belongs to C01. So this relation 4 will also be true for these two functions g and 0. So it is coming this, and after solving we will reach to this step. G norm is less than equal to g norm divided by 2, so it gives g norm is equal to 0. But g norm is what? G norm is the supremum of g of x mod x belongs to 0 1. If the supremum value is equal to 0, then for at every point g of x mod equal to 0, g of x mod equal to 0, it implies gx equal to 0 for every x belongs to. So g is a identically 0 function. Okay, so this implies that g is identically 0 function, but it is a contradiction because we have taken that g is non-identically 0, but we are getting g is identically 0. So this contradiction confirms that there is no such g which is non-identically 0 and it lie in S. So therefore S contains only the 0 function. So S is a singleton set. S is a what set? Singleton set. Therefore the option 3 is true. The option 3 where therefore the option 3 is true. Means t has unique fixed point and that is nothing but the 0 function. The moral of this question is that in this question you can observe a very interesting thing. In this question t is our operator t is not a contradiction. No, not contradiction, contraction. Our operator t is not a contraction. We know that in a Banach space, if the operator is mapping from the same space to the same space, and if it is a contraction, then we concluded that it should have unique fixed point. But in this question, the interesting thing is that this given operator is not a contraction, but still we are getting the unique fixed point here. Unique fixed point here, fixed point is unique. That is nothing but the zero function. But here we are getting unique fixed point due to the contraction of the operator t square. Means you can conclude that whether t is contraction or not, it does not mean. If we can find any power of t which is contraction, then we can conclude that it should have unique fixed point. So I hope that you should remember this main point. This main point is that if t is an operator which maps from the same space to the same space, and this space is a Banach space, along this, if one thing is given that any power of for some power of t, if that power is a contraction, then we can conclude that it should have unique fixed point. Unique fixed point means there is no necessary that the operator t should be contraction. Our necessary is that if we can find some power of t which is contraction, then we can conclude that the operator t should have unique fixed point. I hope that you all understood it very well. Thank you. See you next time very soon. Bye bye.